Good evening. Today we'll talk about the solar cell characteristics. So as a start, we will this is our solar cell. It has this is the effective material that we have, and as we said, this effective material, which is made of semiconductor, will absorb the light from the sun, the photons, and these photons will generate an electron and hole pairs. Okay, so how can I get now separate this electron hole from each other? Because if I leave them there, they will be recombined again, and I will lose both of them. So how can I do this separation? Uh, the first thing that we can think about is we can apply a voltage, but applying a voltage means that we are giving this cell an extra energy or extra power, but we need to get a power out of this solar cell. So another idea that we can use is using the BN junction. So as you may remember that when an N type and a V type semiconductor come into contact, because we have this B type, it has an extra hole, and the N type has an extra electron in its crystal structure. We are not talking now about the charge. They don't have extra negative charge. They have just in their, is if you remember how the N type are made, you will have an extra electron in the extra free electron in the crystal structure, while the B type will have an extra hole. So when they come into contact, we can see here that this extra electrons can move to the other side of the B type and combine with them. This will make the N type side with has an ions, positive ions, while the B type will have a negative ions on the boundaries. Okay, and this we called it the depletion region. I have now a built-in electric field. I can use this idea to have a built-in electric field other than applying a voltage. So I have this voltage that is built-in voltage in the BN type. So as you can see here, this case before I have any light, this is what happened. This is the barrier that we have, the barrier potential that I have. Now, what happened when I apply the light, or when this semiconductor will absorb the light? So before this, what we will do, we have this material here, as you can see. This is our semiconductor material that will generate the whole electron pairs, and we just put it between the N and the P type, so we can get this potential, or what we call it, we can get benefit of this voltage that we have, or built-in barrier. So what happened now, when this semiconductor absorbed the light, the electron hole will be generated, and because of this voltage, now we can see that the electron are going to move to the positive side, which is the N type now, because of what happened, and we have the holes will move to the uh, B B type side. So in this case, I will have an opposite voltage, or an opposite current. So I have one current, and then I have the opposite one because of that happened because of the light. Okay, and at some point now, there will be an equilibrium between these two currents, and then I will have in this case the maximum voltage that I can get of my solar cell, which we call it the open circuit voltage. So we will move now step by step, so you will understand the open circuit and the short circuit. Now, how can I represent my semiconductor, or sorry, my solar cell? Uh, we can represent it by um, a real diode here, which represent this barrier that is built in inside my cell, and I have an ideal current source which represents the solar the current that caused by the solar absorption. And of course I'm gonna need a load here, so I can study the power that can get out of this solar cell. And of course it's depend on the voltage between this terminal of the load, and depends also on the current. So we have two important conditions. The first one is I have something we called it the short circuit, and this happened when the current flow in with the terminals, when the terminals are shortened together. And we have the open circuit, which happened when we have the voltage are left opened without a load. So again, if you can look at this part here, as we said, we already have before we having connecting anything, before we connect anything, because of the BN junction, or we called it the BIN junction because of the semiconductor that we have. It's a BNI junction. After absorbing this light, I will have um, a certain voltage, a certain built-in voltage in this case. Um, so in case that I didn't have any connection here, or if I have a very big resistance, I will end up to with no current flowing in this direction. It's a very big sorry, it's an open circuit, or I have a very high resistance, so I have no current here. I have the maximum voltage that I can get out of my solar cell, and this is what we call it, the um, the open circuit voltage. Okay, so um, this is our case. Now this picture here represents the ideal case of my solar cell. When I will neglect that I have any losses, any resistance, I will just consider that I have the BIN junction. Okay, and this is the part we talked about, the open circuit that happens because of the two currents, the forward and the drift currents, and the voltage that happened between both of them. Now the other case. Now what happened if I disconnect this open part here with a wire? So I will just shorten the circuit, and I cause a current to move. To flow, sorry, with no resistance. So in this case, I will have the voltage equals to zero, while I have the current is maximum. So this is the highest current that I can get out of my solar cell. Okay, and of course, this is dependent on the collection of the light generated carriers. Now, this is the short circuit, the open circuit. Both are very important characteristic of your solar cell. And we have something else. As we said, we dealt with the ideal case. Now, if I'm talking about the real case, I always have some resistance. The internal resistance that I measure consists of two parts. One of them is the shunt resistance and the series resistance. So the series resistance, as we see, is connected in series. Okay, it's mostly because of the context. We will study this later, that each solar cell will need a contact in order to move this charge outside. So mostly they are because of the contact resistance. Now, the shunt resistance is mostly because of the defects uh, as they are making these cells. And the shunt resistance is represented by a resistance that is in parallel with my diode. Um, so what I will measure in my experiment is the internal resistance, which is consist of both of them. Um, how can I measure this, as we are working in the lab, um, we are going back here when we talk about the open circuit. How can I measure the open circuit? I will have my solar cell, and I need to make this circuit open, so I will remove the load. I have no load at first. Then I will can connect my cell to a voltmeter. Now the voltmeter will have in يعني inside it has a very high resistance. So in this case, the voltage that I will measure is the open circuits, because first of all we don't have any load, but we have a very high resistance. uh, Now in the short circuit, uh, I will do the another thing, something else. I will just connect my solar cell to the ammeter, and then I will just use the jumper to make a short circuit. In this case, I will have no load again. So now I have the open circuit voltage, the short circuit current. I can find the internal resistance by taking VOC over ISC, which is the voltage of the open circuit over the current of the short circuit. And this is how I get the internal resistance. And that's it for today. Thank you.